Welcome to my thesis talk on the QuadPlane Small Uncrewed Aircraft System. Advanced Air Mobility, or AAM, aims to improve today's transportation system using electric vertical takeoff and landing aircraft and small uncrewed aircraft systems, or SUAS. Key operations include passenger transport via air taxis and package delivery using SUAS. Among the proposed designs, lift and cruise aircraft are the most popular as they combine the benefits of efficient forward flight with hover capabilities. These aircraft have three flight modes, vertical or lift mode, forward or cruise mode, and a third mode that handles the transitions between the two. I developed the QuadPlane as a scale lift plus cruise SUAS so we can study the unconventional aerodynamics of these emerging aircraft. The first goal for this dissertation was to develop a prototype aircraft with efficient forward flight and vertical takeoff and landing capabilities. The QuadPlane was designed with a fixed wing and with forward and vertical thrust modules for this purpose. For eVTOL vehicles, flow interactions between the downwash from the forward motor, vertical motors, and the vehicle structure make it challenging to use conventional multicopter or aircraft models for modeling their aerodynamics. Measuring thrust and aerodynamic forces in hover, cruise, and hybrid flight conditions is therefore essential to develop an accurate full envelope dynamics model. Next, as lift plus cruise aircraft operate in three flight modes, each with its own different aerodynamic flow characteristics, they require distinct guidance and control methods. Performance comparison across flight modes would provide insights for identifying energy-efficient operational regimes. Finally, as any combination of the three flight modes can be chosen over the course of a mission, the challenge is to choose the most energy-efficient combination, considering transition and performance constraints. This slide provides a brief outline for the research approach adopted for this dissertation. In Chapter 2, we first show the QuadPlane design, build, and validation flight tests. Wind tunnel testing enabled us to measure the aerodynamic forces and moments, as well as dynamic thrust, power consumption, and energy consumption in hover, cruise, and hybrid flight conditions, which is all essential to develop an accurate multi-mode dynamics model for the vehicle. In Chapter 3, we utilize the unique aerodynamic characteristics of lift plus cruise aircraft to create energy optimal trajectory solutions between hover waypoints with and without winds. Chapter 4 describes multi-mode waypoint trajectory generation, distinct guidance and control strategies developed for lift plus cruise aircraft, as well as a novel energy-aware coverage path planner. Let's dive right into Chapter 2, wind tunnel testing and aerodynamic modeling. This will be a summary as the committee has seen most of this work already. I designed the QuadPlane as a VTOL SUAS with a square quadcopter layout simply superimposed on a conventional fixed wing airframe. It was sized to be small enough to conduct wind tunnel tests at the University of Michigan. It has three flight modes: quad for takeoff, hover, and landing, plane for cruise, and hybrid for transitions between the two. Wind tunnel testing enabled us to collect aerodynamic and propulsion system force and moment data in each flight mode over a wide range of airspeeds, angles of attack, motor thrust, and control surface deflections. Using this data, the full multi-mode aerodynamic and propulsion system model was developed for the QuadPlane. Here I'm showing a quick short flight video where we see the full sequence flight. Right there, you would have noticed that the front motor turns on, moving into hybrid mode where the aircraft will accelerate. Here we see the aircraft cruising, and in this instance, the vertical thrust motors are in their idle position. Finally, when the aircraft is getting ready to land, the front motor turns off, which we would see right there. And finally, we move back to quad mode for landing. Related work to Chapter 2 is shown here. Wind tunnel testing has enabled aerodynamic and propulsion system modeling for more than half a century at this point. Aerodynamic models are available for conventional aircraft, multicopters, and some lift-augmented multicopter designs. But the emerging lift plus cruise aircraft have almost no publicly available wind tunnel data. Here I present some of the key results and conclusions from Chapter 2. Wind tunnel propulsion system tests showed clearly diverging trends for vertical and forward thrust, dynamic thrust with respect to forward airspeed. As we can see here, the vertical thrust was found to be higher than static values at the higher airspeeds, and the forward thrust was found to be lower than static thrust at the higher airspeeds. This is indicated by alpha p, which is the propeller angle of attack. Wind tunnel tests also revealed that the quad plane has a natural pitch up tendency in appreciable forward airspeeds due to asymmetric flow from the front to the back. The models and methods presented in this chapter can serve to inform future control systems as well as future lift plus cruise designs. Also, I would like to point out that the multimode flight dynamics model that we developed in this chapter is used throughout the other two chapters as well. So more results from this chapter are actually embedded in later slides. Let's now move on to chapter 3, optimal traversal between hover waypoints for lift plus cruise aircraft. In this chapter, after related work, we first define the general traversal between hover waypoints in no wind. Next, we present energy consumption, followed by optimal traversal in no wind. After that, we will expand our discussion to include steady wind. We first discuss straight line traversal between hover waypoints and the constraints on straight line traversal in steady wind, of course. And finally, I will present quad plane case study results. Now, autonomous transition schemes, such as those described in the reference literature, allow for reliable transitions between vertical and forward flight, which is key for multimode flight operations. Work has been done to derive energy optimal trajectories with operations involving constant and accelerated flight, but all of these studies assume operations only in a single flight mode. Lastly, we reference maneuver primitives here, which we actually use in this chapter, and we'll describe them later on. Let me start by defining general traversal between hover waypoints in no wind. In addition to the no ambient wind assumption, we also assume straight and level flight and that the heading can be adjusted at the hover waypoint Wi to point directly at Wi plus 1. These assumptions let us simplify the problem and focus on pure longitudinal flight. A general traversal trajectory would consist of an initial accelerated segment from hover at Wi to Vc, airspeed Vc, which is the cruise airspeed, an optional constant airspeed segment at Vc, and a final deceleration segment from Vc to hover as we reach Wi plus 1. The data structure defining general traversal between the hover waypoints is given here. Tau plus represents the acceleration, Vc represents the cruise, and tau minus represents the deceleration segments. Now, each parameter in this data structure was carefully chosen to completely represent the accelerated segment. We will go through the individual parameters in the next slide. Also, please note that Vc star is the most efficient cruise speed for the aircraft, and that path length between Wi and I plus 1 is given by Li I plus 1. These variables will be used later on in the slides. The main benefit of using hover waypoints is that hover waypoint trajectories can be analyzed segment-wise, and therefore it simplifies the overall process. Now let's look at the parameters of tau k in detail. Vc is the airspeed at the end of the accelerated segment, which is shown on the right here. If there is a cruise segment, Vc is held constant over that segment after the accelerated segment. Amax k is the maximum slope of the cubic spline airspeed profile. K equals plus indicates acceleration and k equals minus indicates deceleration. A lim k represents the acceleration and deceleration limits of the aircraft itself. And VQH and VHP represent the transition airspeeds for quad to hybrid and hybrid to plane mode respectively. These last two parameters is what is novel to this work as we support multi-mode flight over this accelerated segment. So as you can see from this equation, the aircraft flight mode from 0 to VQH is quad mode, from VQH to VHP is hybrid mode, and beyond VHP, we operate in plane mode. Now, as this cubic spline airspeed profile is completely constrained, we can analytically derive the four cubic spline coefficient parameters, and consequently, we can compute the time and distance traveled over the accelerated profile. Now here I show the full airspeed profile for the general traversal. You can see if we increase VC while keeping Amax plus and Amax minus the same, the cruise segment would become shorter and shorter. In the limit, the traversal would have no cruise segment, and acceleration would be immediately followed by a deceleration segment. In this case, the VC that we get is also known as the Vmax, which is the maximum achievable airspeed for that segment length, given Amax plus and Amax minus. Looking at this from the other side, to be able to reach a given airspeed, say the best cruise airspeed, VC star, in the shortest distance possible, traversal should involve an acceleration followed immediately by a deceleration. Now, as the cubic spline airspeed equations are completely known, we can compute the distance traveled over the accelerated segments, and thereby we can show that these equations represent Lmin VC star and Vmax. Next, let's look at the total energy cost for general traversal in no wind. The total energy is basically the sum of energy consumed over the accelerated, cruise, and the deceleration segments. The cruise segment can be simplified. Energy over the cruise segment can be simplified by this equation, where we introduce the parameter called energy per distance, which is simply the power required to maintain a given airspeed, normalized by the airspeed itself. Multiplying this with the cruise segment length gives us the total energy over the cruise segment. To get energy over the accelerated and decelerated segments, we need to integrate the instantaneous power over the accelerated segment. And here is where the aeropropulsion model developed in chapter 2 helps us, because we have equations for those available. Next, let's see what it takes to derive the energy optimal solution. So here I show a multivariable optimization problem, which plays with the cruise airspeed Amax plus and Amax minus to minimize the total energy covered over the traversal. This is subject to the following constraints. The first constraint basically says that the cruise segment can be non-negative. The second constraint we have already kind of talked about, that VC has to be less than or equal to Vmax. And of course, this has to be lesser than the aircraft's airspeed limit, which is Vlim. The last two constraints limit the maximum acceleration or deceleration over the cubic spline airspeed profile to be within the aircraft's acceleration limits. In the journal paper for this chapter, we present a lemma, lemma 3.1, which basically explains the solution for the traversal equation. What we do here is basically the problem is divided into two main cases. You can feel free to read the lemma if you want, but I will just summarize that in simple terms. The problem is divided into two main cases based on the existence of solution critical points. If a solution critical point does not exist within the domain, then we consider two subcases. For segment lengths that are less than Lmin VC star, this means that the segment is actually too short to reach the best or most efficient cruise speed. In this case, the optimal traversal is given by an acceleration segment to Vmax, which corresponds to Lii plus 1, followed immediately by a deceleration segment with no cruise segment involved. If, however, the segment length is longer than Lmin VC star, then the optimal traversal comprises of an acceleration from hover to VC star, cruise at VC star, followed by deceleration from VC star back down to hover. Finally, for the case when a solution critical point or more solution critical points do exist, we actually need to compare the total energy for traversal at each solution and boundary critical point, and then select the one with the minimum energy to give the optimal traversal. This lemma also tells us that it is always best to maximize acceleration magnitudes, that is to reach cruise or hover quickly in order to minimize traversal energy. For those who are interested, the formal proof for this lemma is in the journal paper, and I can go through it if the people want to look at it later on. Now that we have optimal traversal in no wind, we expand our analysis to include steady wind. Lift plus cruise aircraft have to point directly into the wind at hover in order to maximize stability and efficiency. Also, as the airspeed changes to track a reference ground speed, the heading must also change accordingly. The relationship between ground speed, airspeed, course angle, and heading is given in terms of the wind magnitude and direction in these two equations. Now, the data structure, which defines straight line traversal between hover waypoints, is adjusted to include wind effects. We notably see the superscript W for the accelerated segments, and we replace VC by VGC, which represents the ground cruise speed. Also, the accelerated data segment is again adapted for steady wind operations, where VC becomes VGC, ground cruise speed. A max becomes ground acceleration limit over the cubic spline. AA lim is the acceleration limit for the aircraft itself. VQH and VHP basically get an A to represent airspeeds for transition between quad to hybrid and hybrid to plane. And we have to add these three parameters, which is the wind magnitude, direction, and the heading rate limit of the aircraft to completely describe the accelerated segment in steady. Now, there are constraints that exist on straight line traversal in steady wind. And if we do some calculus to the equation that we just showed for the relationship between airspeed, ground speed, and wind speed, we can surmise that the rate of change of heading actually depends on the rate of change of airspeed, the airspeed itself, and the relative wind angle, which is course angle minus the heading of the wind. This is easy to derive, but it requires some calculus steps. And of course, this heading rate is limited by, the aircraft's performance limits and must lie between sigma.lim and minus sigma.lim. Now, in order to check these constraints, in the paper, we actually developed two algorithms which work in parallel. The way this works is surmised here. We basically start with the ground speed and ground acceleration values corresponding to the best cruise airspeed and aircraft acceleration limits. The airspeed rate and heading rate are computed, assuming straight line traversal between the adjacent hover waypoints. Constraints are checked to determine feasibility of straight line traversal. If feasible, the straight line trajectory is generated. If not, we actually reduce the ground speed and the ground acceleration values, and we repeat this process. These iterations keep running until a minimum value for ground speed or a minimum value of the ground acceleration is reached. If the constraints are still not met, then that means that the straight line traversal is actually not feasible, and maneuver primitives are required for traversal. Maneuver primitives are basically kinematic transformations which take the vehicle from the current to a desired state. We describe an example maneuver primitive in this work, which uses cubic splines in the course and ground speed. We will see this in the results later. Now let's look at optimizing the energy consumed over straight line traversal in steady wind. The energy cost is simply the sum of energy consumed as we saw before. The constraints are basically adapted from the no wind case. Airspeed and ground speed constraints are separated out. Okay. Airspeed and ground speed constraints are separated. VG max is the maximum ground speed acceleration over the cubic spline. And VA lim is the maximum aircraft airspeed. We also constrain the rate of change of airspeed between the aircraft acceleration limits, and we have seen this constraint before. The last constraint is actually put on the wind magnitude itself, so that we can actually hover in quad mode at the hover waypoints. My laser pointer is stuck. Oh, there we go. Next, we will present QuadPlane case study results. We start by describing QuadPlane power in steady and accelerated flight. This enables us to compute the energy consumed over the general traversal. Then we describe the optimal traversal between hover waypoints in the QuadPlane in no wind first, and then we show traversal in steady wind along a straight line, and also in a case where straight line traversal is not possible using maneuver primitives. These are the quad plane parameters. We have seen all of these symbols before, and for the quad plane, these are the values where the aircraft switches from quad to hybrid mode at 2 meters per second, hybrid to plane at 12. This is the airspeed limit for the aircraft. This is the best operational airspeed. The maximum ground speed limit, the maximum ground acceleration limit, and the aircraft's acceleration limits are these. And finally, this is the heading rate limit for the aircraft, for the quad plane. Here, we are plotting power consumption for the quad plane in steady flight across the 3 flight modes. As expected, hybrid mode consumes the most power for a given airspeed. Plane mode near 12 meters per second consumes the least power. This is actually less than the hover power in quad mode. So it is actually more efficient to fly in plane mode at 12 meters per second than it is to hover at a single point. Also, we can see how the hybrid mode airspeed range overlaps the quad and plane mode ranges, and thus we can transition from quad to plane via the hybrid mode. Here I'm showing the energy per distance values across the 3 flight modes. Recall that energy per distance is power divided by the airspeed. And this plot basically gives us a better sense for choosing airspeeds for energy efficient traversal than the power plot. Energy per distance across quad and hybrid modes decreases monotonically as airspeed increases. And we see that energy increases monotonically in plane mode. This is how we actually determine that 12 meters per second in plane mode is actually the best cruise airspeed. These plots show us the instantaneous power consumed in accelerated flight as a function of airspeed and the instantaneous acceleration. These were derived using the propulsion system model from chapter 2. And also we conducted force balance to accommodate the different acceleration values. As VHP equals VC star, most of the acceleration and deceleration only occurs in quad or hybrid modes, and so we don't show plane mode acceleration plots here. Also note that for hybrid mode, we show data for 0 pitch angle. Now that we have all of that information available, we are able to compute the total energy over a traversal for the quad plane. Across these 2 plots, we are plotting the total energy as a function of cruise velocity for different acceleration Amax plus and Amax minus values. And the multicolor plots that you see here correspond to different segment lengths. What you can clearly see is that as airspeed increases, the total energy for traversal decreases, as we showed in the lemma. Also notice that we only plot VC values or cruise airspeed values less than Vmax. And that is the reason we don't see the segment length of 10 meters on the left plot, because 10 meters is actually too short to reach a cruise airspeed of 2 meters per second given these acceleration values. Next, I'm showing the same total energy as a function of cruise velocity, but here we plot different acceleration magnitudes. And we can clearly see that the higher the acceleration value, lower is the total energy across both of the segment lengths. Finally, here I am showing the optimal traversal airspeed and the maximum cruise airspeed as a function of the segment lengths. Here we can clearly see the 3 cases that we talked about in the lemma. Let me start by showing, let's start by looking at segment lengths which are longer than L mean cruise, that is the segment lengths where VC of 12 meters per second is actually achievable. What we see is across all of these, the energy optimal airspeed is chosen to be 12 meters per second because that actually optimizes the total energy consumed. For the cases where this airspeed cannot be reached, we have 2 cases. For these cases where basically the first, third, and fifth one, the first, fourth, and fifth one represents the non-existence of solution critical points. So the boundary critical point, that is Vmax, is chosen as the energy optimal airspeed. However, for these two segment lengths, we see that a solution critical point actually exists, which minimizes traversal energy at an airspeed lower than the maximal possible airspeed. And we see a similar trend for both the acceleration values.
Hey, Akshay, I hate to interrupt you, but I don't know
Yes.
if it's true for other people. I'm not seeing a laser pointer on my screen.
Oh, really?
Oh, there it is, but I wasn't seeing it before. Maybe others were.
Okay, this is a little tricky.
Yeah, it just popped up for me, but oh, it disappeared again. Oh, I think maybe
Okay.
or something. Yeah.
Okay, I'll try to fix that. Okay, thank
Yeah,
you.
so when you were saying this, we didn't know what this meant.
Oh, I'm so sorry. Okay. All right, let me re-explain then. So these two airspeeds, these two segment lengths have optimal energy airspeeds at the Vmax limit because solution critical points do not exist for these particular segment lengths. However, for the second and the third segment lengths, we do see that a solution critical point exists, which minimizes traversal energy at an airspeed lower than the maximum possible airspeed. Okay. Let me go on to the next slide. So now we will look at quad plane case study results in steady wind. For all of the remaining plots, we consider a segment length of 500 meters and a wind magnitude of 4 meters per second. This plot that we see here was generated for relative wind angles from -180 to 180 to cover the entire suite of possibilities. And we set a minimum ground speed, minimum ground cruise speed to a very, very low value just to enable traversal. The green zones in this plot indicate that the straight line traversal in steady wind is feasible, and in the red zone, straight line traversal is actually not feasible. I will next show a case in the green and one in the red zones. So here is delta equals 90 degrees, which was way up there. So green, it lies in the green zone. And we can see that straight line traversal is possible here. The wind field is pointing towards the north, and we are trying to traverse along a course angle of 90 degrees from the left to the right. So here, notice that the heading starts at 180 degrees relative, which is basically the aircraft pointing downwards relative directly into the relative wind. And airspeed starts at 4 meters per second to compensate for the wind speed in order to hover at the initial waypoint. Over the accelerated segments, the heading rate varies smoothly and is symmetric between the acceleration and deceleration segments as expected, and it remains well within the limits. And that's why the straight line traversal is actually possible for this case. Over the cruise segment, the quad plane actually crabs into the wind, and we see the heading is about 110 degrees, which is 20 degrees offset into the wind in order to be able to track the straight line. Notice that the power consumption trends increase and then start falling. The peak of this instantaneous power consumption is seen when the airspeed acceleration is actually the maximum, which is somewhere around the middle here. And we see the sudden drop in the power consumption when the airspeed reaches 12 meters per second, and we are able to transition to plane mode, which is much more efficient. Here I'm giving some benchmark data, which we basically compare with our quad plus hybrid plus plane solution that we just saw, and we're looking across different options that are possible. First, we look at quad mode only across this traversal, and we choose a cruise airspeed of 6 meters per second, which is actually close to the best energy per distance value for quad mode. And we can see that the energy consumed is really high, which is probably expected. Next, we consider plane mode only, but the caveat here is that there is no hover. Essentially, what this means is the aircraft just flies straight through those two waypoints without slowing down or stopping or anything like that. It is basically a constant 12 meter per second plane mode operation. And of course, the energy is really low here. Next, we look at a quad plus hybrid solution where we do everything that we did for our optimal traversal, except that we do not transition to plane mode when we reach 12 meters per second. And finally, we look at a quad plus hybrid plus plane solution, which actually gives us the best energy savings while also hovering at the waypoints. Note that all of these energy savings are relative to the quad mode total energy value. All right, now let's look at the case where this point basically lies within the red zone where straight line traversal is not possible. Here we are using maneuver primitives which use cubic splines in the course angle and ground speed. This maneuver is designed so that the heading rate constraints are not violated over this maneuver. Full details on how this works are available in the paper, and I can go into more details if anyone is curious or if we have extra time at the end. Here, notice that the course angle and the heading start off at the same value. This is by design. This is how the maneuver primitive is actually designed. And notice that the maximum rate of change of heading maximum rate of change of course angle or chi dot max is actually 25 degrees, which is what we set for the maneuver primitive. When following this traversal trajectory, the heading rate actually stays within the limits, and that's what we want. Again, the power trends follow the acceleration in airspeed, and we see a sharp dip in the power when airspeed reaches 12 meters per second and we switch to plane mode. In summary, for this chapter, we were able to derive energy optimal traversal solutions for any eVTOL aircraft. And we can do this. In order to do this, we basically need energy consumption data for accelerated and cruise flight. The Lemma 3.1 presents us with a case-by-case solution to the optimization problem with no wind. And we also presented constraints on straight line traversal in steady wind. Wherever straight line traversal was not possible, we showed how we basically showed an example cubic spline maneuver, which can enable the traversal. But please note that this maneuver primitive was not optimized and can be further optimized for more energy savings. Now let's move on over to chapter 4, multi-mode flight simulation and energy-aware coverage path planning. In this chapter, we use the aerodynamic and propulsion models developed in chapter 2 to describe quad-plane dynamics. Quad-plane dynamics actually help us to determine trim states in each flight mode, which is essential for control design. 4 waypoint types are described along with trajectory generation methods. Next, we describe a novel energy-aware coverage path planner, and we present quad-plane guidance and control models. Finally, we show the results for the quad-plane. So in this chapter, we build upon the dynamics and control modeling methods that are shown in literature. 2 of the 4 waypoints that we describe in this chapter were actually first introduced by the FAA for conventional aircraft. These are the flyover and flyby waypoints. And of the 3 guidance methods shown here, we chose the carrot chasing algorithm, and we modified it for quad plane guidance. Here I'm showing the quad plane state and control vectors. The quad plane dynamics are governed by the 6 degree of freedom nonlinear equations, which we'll look at in the next slide. The quad plane is controlled by a combination of the plane control vector, or UP, which comprises of normalized control surface deflections for aileron, elevator, and rudder, as well as the forward thrust value. The quad rotor or quad mode control vector includes the vertical thrust from the 4 vertical motors, M1 through M4. These are the nonlinear 6 degree of freedom body frame equations. And the important part here is how we get the forces in the body frame acting on the quad plane and the moments that act on the quad plane in the body frame. And these forces and moments are actually derived from the model that we computed in chapter 2. The aerodynamic and propulsion system forces and moments in the body frame are added together to apply to that equation. Here you would notice all of the orange colored coefficients are actually derived from the wind tunnel, and we augmented this with these blue terms, which are NACA data for the vertical stabilizer, in order to give us some side force and in the side slip conditions, basically. So trim states are essentially equilibrium conditions where all the forces and moments are balanced. We performed the trim analysis for each of the flight modes, quad, plane, and hybrid. And some of the important constraints on the state and input are listed here. We limited the side slip to plus minus 1 degrees. We limited the forward and vertical thrust by the experimental dynamic thrust limits that we obtained from chapter 2. And we also limited the control surface deflections by the actual angular deflections on the quad plane prototype. In order to get the trim states for the different flight modes, we described distinct cost functions, and we were also able to set the desired pitch angle independently for hybrid mode trim states. So here we describe the 4 types of waypoints that we use in our study. Flyover and flyby waypoints are described by the FAA. Hover waypoints are uniquely defined for VTOL capable aircraft, as the aircraft can hover in space. This allows the aircraft to adjust the heading at a given waypoint to directly point at the next waypoint, and thus it can very accurately track the ground track. We introduce fly coverage waypoints, which are inspired by coverage paths. And these basically require the aircraft to match the heading of the next segment as it reaches and passes over the given waypoint. This turn is executed as a 2-part cubic spline turn to ensure that the states stay smooth. Here, I will describe a trajectory generation methodology. So our trajectory generation method basically creates this trajectory matrix, which has time synchronized earth frame positions and velocities, as well as the desired pitch angles, which are actually only used in hybrid mode. We also have the desired flight mode as part of the trajectory matrix. These trajectories are generated for the type of waypoint specified. And the trajectory generation function also handles transitions between quad and plane modes by inserting cubic spline pitch and airspeeds from the quad and plane trim values. Also, please note that we assume that the wind field is constant and it is known a priori. Next, let's jump into the description of the energy-aware coverage path planner. This planner basically balances energy consumption and coverage over a set of waypoints. I will describe coverage in the next slide more formally. But basically, hover waypoints maximize the coverage, while fly coverage waypoints minimize the energy consumption as they allow the aircraft to stay in plane mode. The flight plan always starts and ends in hover waypoints, and the cost trade-off for coverage and energy consumption is computed over all intermediate waypoint sequences. So basically, in a n waypoint trajectory, we have 2 to the n minus 2 possible waypoint sequences, considering each intermediate waypoint could either be hover or fly coverage. Now, in order to compute the cost, we first described normalized cost metrics for the energy consumption and coverage. And coverage is basically defined as the ratio of the segment length as the ground track distance covered by the trajectory as a ratio divided by the total the total straight line ground track distance. The cost for the kth waypoint sequence is defined with this weighting factor xi, and the waypoint sequence with the minimum cost is selected for each given weight. I will show the results for this later on. Next, let me quickly describe our quad plane guidance method. The carrot chasing method conventionally uses a fixed distance to set a virtual target ahead on the desired path. For the quad plane, we basically moved that from a fixed distance to an adjustable time horizon. The adjustability of the time horizon allows us to provide a trade-off between tracking accuracy and control robustness, because a shorter time horizon favors accuracy, while a longer time horizon favors control robustness. Also, zero side slip is desirable. So the quad plane points into the relative wind in hover, and it crabs into the wind otherwise. For the quad plane control scheme, we used textbook cascaded PID control for both quad and plane modes. Notably, plane mode uses the elevator to track altitude. Airspeed in plane mode is tracked using the forward motor. Quad mode uses vertical thrust to track altitude, and airspeed is tracked using quad rotor pitch commands. Now, our hybrid mode combines quad and plane mode controllers in such a way that altitude is tracked using the quad mode controllers, which is by vertical thrust, and airspeed is tracked using the plane mode controller. So this leaves the elevator and the quad rotor pitch commands free to track pitch independent of trajectory following. This is a schematic for the sustained hybrid mode control scheme, because in addition to providing transitions between quad and plane modes, we can also operate the quad plane in sustained hybrid modes, which allows us to access airspeeds which are not accessible to quad or plane modes. So these control loops are part of the quad controllers, and these other ones are part of the plane controllers. Next, we are going to look at quad plane results, and we will first look at some trim states for cruise and turning flight, followed by endurance and range for the quad plane. Then I will show you one example for trajectory tracking, and then we'll dive into the energy-aware coverage planner results. So here are some of the trim states obtained for the quad plane across quad, hybrid, and plane modes for cruise and turning flight. We also see the corresponding power and energy per distance stats here. As you can see, operations in plane mode at 12 meters per second are the most efficient. Also, if you notice that a transition from quad to plane with VQH speed being 2 meters per second requires that the pitch angle changes from around -1 to +5 degrees. And this is handled by the hybrid mode by providing a smooth cubic spline between those pitch values, which is tracked in hybrid mode. Next, we'll look at the endurance and range plots for the 3 flight modes in the quad plane. As expected, plane mode actually performs the best in both endurance and range. We also see multiple plots for hybrid mode here, and these different plots correspond to the different pitch angles that are set for the hybrid mode to track. Now here is a trajectory tracking example in quad mode with hover waypoints. Now, interesting things to note here. First of all, we command a cruise ground speed of 2 meters per second, and it requires the quad plane to hover at each waypoint. And this is in the presence of a steady wind of 4 meters per second. The most interesting part of this trajectory is the downwind section, where the aircraft actually appears to be flying backwards from the ground frame of reference, even though the airspeed is maintained at 2 meters per second. This is basically a consequence of having a wind speed higher than the commanded ground speed and the aircraft pointing into the relative wind direction. Next, let's look at the energy-aware coverage planner results. We used 7 random waypoints, which were generated over 1,000 by 1,000 field. And so there are 5 intermediate waypoints, and so 32 possible waypoint sequences, with each intermediate waypoint being either hover or fly coverage. With the cost metric given here, we basically did a sensitivity analysis and increased the weighted factor xi slowly from 0 all the way to 1. At 0, the cost function favors coverage. So we see that all of the intermediate waypoints are set to hover. At 1, the cost function favors energy consumption. So we see the minimum energy consumed of all of the cases here. And all of the intermediate waypoints are fly coverage here. Now let's look at all of these individual trajectories separately. So here, I am going to keep increasing xi slowly as we move through these different options. As we saw before, for xi at very, very low values, not almost, all of the waypoints are actually hover waypoints. So the aircraft accelerates and decelerates going between hover to hover waypoints. These are optimal traversal trajectories. Also note that these colors actually represent the flight mode. So dark blue is quad mode, which we only see in the airspeed plot because it's just so small. Quad to plane is yellow, plane to quad is red, and light blue is plane mode. So what we notice here, going from the first to the second category of xi values, is that this particular waypoint became a fly coverage waypoint from hover, and we lost this deceleration and acceleration phase, which actually favors energy consumption at the cost of a small coverage loss. And this is what we see throughout. Here we see that this particular waypoint has been converted to fly coverage, and so on until we reach the final case where all of the waypoints are now fly coverage, and we only accelerate at the beginning of this trajectory and finally decelerate at the end of the trajectory. Next, here I'm showing the Pareto front for the energy-aware coverage planner for this particular example. All of the blue X's show the possible solutions, and the red stars show the optimal balance between minimizing energy consumption and maximizing coverage. On the y-axis, we have the cost function for energy, and on the x-axis, we have the cost function for coverage. Concluding the fourth chapter, we basically did steady state analysis and the simulations for plane mode. And we saw that plane mode is basically the most efficient for flying over long distances. It's actually 33% more efficient to loiter as an aircraft at 12 meters per second than while hovering. The quad plane can operate at almost all airspeeds. Why do I keep saying almost? The quad plane can operate at all airspeeds between quad and plane modes in hybrid mode. Guidance and control schemes allow us for tracking trajectories with low errors, and it supports unconventional flight conditions such as the backwards quad plane motion that we saw. And finally, the energy-aware coverage planner provides us with a trade-off between energy efficiency and coverage over randomly generated waypoint trajectories. Overall, the QuadPlane SUS enabled us to experimentally validate the multiple model aero propulsive model that we developed for the lift plus cruise aircraft. Wind tunnel tests provided us with novel insights into aerodynamics of lift plus cruise aircraft. For instance, the natural pitch up tendency that we see with the quad plane. Quad plane model and trim analysis allowed us to develop control and guidance schemes specifically tailored to lift plus cruise eVTOL. And energy and power consumption modeling enabled us to develop some novel energy efficient flight planning methods for lift plus cruise aircraft. The energy aware coverage planner, which we just show, and it actually implements the optimal traversal solutions from chapter 3. In future work, lift plus cruise aircraft actually have a natural pitch up tendency, which can be attenuated to facilitate deceleration and transition to hover. AAM aircraft modeling would benefit from more publicly available wind tunnel test data, especially in high side slip conditions. The cubic spline maneuvers that we presented can be optimized in order to get improved energy efficiency for traversal. And the energy-aware coverage planner that we showed will benefit from non-zero climb rates along with 3D wind field and gusts. Before I end, there are a lot of people that I need to thank, without whom I would not be here today. First, I would like to thank every single person who joined me today. I would also like to thank my dissertation committee, Professors Lee, Professor Panagu, and Professor Sarter for their guidance and support. For my advisor and committee chair, Professor Atkins, No words can express my deep gratitude towards you, but I will try. Throughout the years, you've been an unwavering guiding light for me through ups and downs in your own personal life. You have truly been like a mother for me away from home. I thank all of my A to CIS lab mates, old and new, for making my life at UMich fun. Mia, Cosme, I'm sorry. Mia, Cosme, Brian, Jeremy, Prashin, Matt, Prince, Joseph, Paul, Mark, Brandon, Emre, Heejin, Brooklyn, and Epidemi. Thank you all. Also, thank you, Sid, for showing interest in the QuadPlane project and helping me with wind tunnel tests and outdoor flight tests. Prashin, Matt, Prince, Joseph, and my OG Aerospace Masters fam, Vignesh, Smriti, and Rohan. You guys have been my closest friends at UMich, and I cherish all the time we spent together. Also, shout out to the No Thai Pals volleyball group. I would also like to thank Chris Chartier for helping me with wind tunnel tests, Professor Peter Gaskell for giving me the opportunity to be your GSRA. I learned a lot from you. And Denise, for always being there to help us grad students. You're the best, Denise. Finally, I would like to thank my parents and sister who have made me the person I am today, supported me at each step of my life for 30 plus years, and made countless sacrifices to improve my life. All of this was made possible through your love and blessings. To my wonderful wife, thank you for being an immense support. Thank you for your love, sacrifices, and patience, and being my partner through this roller coaster PhD journey. The finish line is in sight, and I can't wait to start the next chapter of our lives together. Go Blue.